Let's take a look at this differential equation here. Now, the lesson you probably just watched was on separable differential equations. You'll recall that in that situation, our goal was to separate the variables in a way that we could get our x's on one side and our y's on the other, and then integrate both sides to get a solution. In this particular problem, however, something unusual is going to happen that's going to put a stop to that process. And let's follow that logic to its end here. So to separate the variables, I can do some cross multiplying. Feel free to hit pause if you're slow on algebra. A lot of people are. And after separating my variables here, you don't necessarily need the 1 on the right side, but it's kind of nice to just remind yourself that dx is the same as 1 times dx, like anything multiplied by 1 is itself. Because then when I integrate both sides, I can easily see that the integral of 1 is x. And while I would get a plus c on both sides, I can just put it on the right side here. But here's the snag in the idea. You probably just watched a video recently on how if we separated the variables, x is on one side and y is on the other, that we could integrate both sides and get a solution. Great strategy. But the problem is, looking at the integral on the left here, that's not an integral that at this point in the course that we can really do. And we'll see strategies later on in the class for integrals like that. But at this point in chapter 6, we are not at a position where that integral on the left side there is really doable. So while it's a great idea to separate variables, in this case it's an unfruitful endeavor because it leads to an integral that we really at this point can't do. Which raises the question then, if we can't separate variables in an effective, meaningful way here, what do we do? Well, at this point, what one should do in the class is simply memorize the logistic curve differential equation here. If you compare our problem to the one above it, you'll see that it's exactly the same format, with k being 2 and m being 6. And right now, we're just going to use the fact that someone has solved this differential equation generically for us. And so all we need to do, it's quite simple, is realize, oh, we're solving the logistic curve differential equation with k value of 2 and an m value of 6. And all we have to do now is plug in k equals 2 and m equals 6 into the solution that someone has cooked up for us. If you're wondering where the equation on the right came from, the y equals solution to this, that's a story we're not getting into now. That's just a formula you memorize for this differential equation. And now it's as simple as saying, okay, putting in k equals 2 and m equals 6 gives me this. And I'm done with the problem. Now, I would be remiss, even though I am done with this problem, if I didn't go on and tell you a little bit about what the logistic curve is. And you probably saw it in pre-calculus, but not in this differential format. If you were to graph this logistic curve, which I've done here, I've graphed it for a particular c value of 10. Not that there's anything special about 10 in this problem, but I just wanted to give you an image here. If I graphed it for a particular c value, it would look something like this. And you've probably seen these in a pre-calculus setting where you were dealing with inhibited growth, the growth of a population that couldn't exceed a certain value. And I just want to point out a few things about the differential equation here that maybe wouldn't occur to you if you didn't hear me say them. So on the far right side of this curve, you'll notice the curve is flattening out. And that y values in this case are getting closer and closer to 6 as we go further to the right. Well, it's worth noting that if we're way off to the right side of this graph, maybe y is 5.9 or 5.99, depending on how far over we are, you'll notice that this expression here in the parentheses would be very close to 0. And therefore, the derivative dy dx would be very close to 0. But doesn't a derivative of 0 indicate a flattening out of a curve? So the idea here is as y gets closer and closer to 6, dy dx gets closer and closer to 0, thereby flattening out the curve. Again, a zero derivative meaning the flattening of a curve. If you didn't follow that, don't worry about it. This is just sort of some advanced thinking to launch you into future parts of the course. Let's analyze the other half of the curve. On the far left side of this curve, as y gets closer and closer to 0, this portion of the differential equation would be closer to 0. And again, dy dx over there would have a value very close to 0 because 2y is close to 0. And the idea here again being, on the far left side of this curve, as y gets closer to 0, the derivative gets closer to 0, meaning there's a flattening of the curve on that side as well. Now, if you understood that differential analysis, that's great. And if you got a little lost in it, don't worry too much, because at this point of the course, all you need to know for the mechanics of these problems is, if you're given a differential equation in exactly this format, you take the 2 and the 6, and what you do with them is plug them in for the m and the k in the formula that you memorized, the one on the right, and you have your solution to the differential equation, and that's all mandatory to know at this point. But all that other understanding of what the differentials mean and everything, I hope you got something out of that as well.